Dr. Rachael Livermore from UT Austin. She recently finished her PhD from the University of Durham before moving across the ocean, where we're trying to cure her of her accent. But apparently she's no trouble doing that now with your boots and your pickup truck. So she's embracing all things Texas, which we generally appreciate. No, she did some great work for her doctoral dissertation on lensed galaxies, studying the properties of them. I think every wavelength you could get your hands on while you were at Durham, before moving over to Austin, where she's been doing some great work with Steve Frankenstein. So she's here to tell us about all of it. So thanks, Rachel.
Well, I'm going to stick to the lensing stuff because that's more complete. Since I've arrived in America, I have discovered that I have this amazing ability, which I think is inherent to British people, of causing skies to become cloudy. So we only very recently managed to get data, and that was actually because I went observing with Nicola, and so we discovered that if you have two British people, it cancels out.
So that's why UK has had such tremendous influence on astronomy, because
absolutely, yeah. So the moral of the story is never take one Brit observing with you. There have to be two. Perhaps it works for all even numbers when we should experiment. So I'm going to talk about gravitationally lensed galaxies and why they're awesome and some of what we learned from them. My title slide is just demonstrating that I have, of course, embraced all things Texas, as evidenced by my pickup truck outside. So what I'm going to talk about, first of all, why we need the high spatial resolution that gravitational lensing can give us. Brief introduction to gravitational lensing for anyone who hasn't come across it before. And then some of the work I've done, imaging galaxies, redshifts 1 to 1.5. We'll then move up to higher redshift, looking at molecular gas at redshift 5, and then star-forming clumps that we see between redshifts 1 and 4. And finally, if I get time, I tend to go quickly over time, I'll talk about the work we're doing now on the Hubble Frontier Field program. So, to start off, this is why we're trying to do what we're doing. This is what you see if you look at spatially resolved images of galaxies at high redshift. On the left is from HST, and then on the right using Symphony on the VLT, so integral field spectrograph. So you can look at the H-alpha emission line across the galaxy. And you can see that they don't look like galaxies that we see locally. We tend to find that the star formation is concentrated in these massive clumps, and the clumps dominate the morphology of the galaxy. So they get called clumpy galaxies, clump clusters. If you see them edge on, like some of these ones, they get called chain galaxies, because it just looks like a long row of clumps. And so what we want to understand is what's going on with these clumps, how do they form, and why do the galaxies look like this, what happens to them. So we know that these clumps are pretty ubiquitous at high redshift on kind of kiloparsec scales, which is not what we see locally. Locally you see stars form in H2 regions which are of order 100 parsecs across, so these are 10 times bigger. The problem is that kiloparsec is the limit of our spatial resolution above redshift 1. So this is the best we can do. Maybe there are also star-forming regions of scales of 100 parsecs like there are locally. We have no idea, we can't see them. So what we want to do is to try to probe further down, look at the finer detail within these galaxies to understand what's going on. Of course, simulations can already do this. So this is simulation by Daniel Severino showing formation of a galaxy where you have these streams of cold gas falling in from the intergalactic medium, and these fall onto the galaxy, form these massive clumps, which then migrate into the center, and then this is what forms the bulge at the center of the galaxy. And you keep up a kind of steady state, although the clumps themselves are very short-lived, of order a gigayear or so as they fall into the center. You then form new clumps on the outside from these cold streams that are falling in from outside the galaxy. This is a very nice picture and has become very popular. There's one minor flaw: these cold flows have never actually been seen, and the community seems fairly divided as to those who believe in them and those who think that they're nonsense. So we want to look at the clumps and try to understand whether this picture is real, whether we see any evidence for them falling in, how limited to the kind of star-forming regions that we get locally.
Rick, do you actually have to have the cold flows to develop the clumps?
Not to develop the clumps, but to maintain them.
To maintain them,
Yeah,
so you use steady
because
state
otherwise
gas.
you would use up your gas.
Okay, so something has to be
and then-
replenishing the gas.
Yeah. So we need to be keeping the gas fractions high. And cold streams are a means of doing that. And
Yes.
spoiler alert, I am not going to confirm all of our cold flows. So there you go.
Don't let anybody leave.
So this is the problem we have when we're trying to look at high redshift galaxies. If we take something like M82, which is a really nice galaxy that you get far more information about if you look at it with spatial resolution, and you can see that has typical outflows and all sorts. But if we put that at redshift 2, it's going to look like that. So we're not going to get any useful information out of that. So what we really need is a really, really big telescope, so we can get the kind of detail we get in local galaxies in high redshift. And this is where gravitational lensing comes in. So this is Phil Marshall's awesome demonstration that really goes down well in schools. If you take a candle flame, any pointish light source, and view it through the bottom of a wine glass, you can see how the glass distorts the light. If you align it perfectly, so you're looking straight through the centre, like this one here, you get the perfect Einstein ring. We very rarely see that in nature, of course, because not only are they not perfectly aligned, but we don't have nice, perfect spherical mass distributions. So what you see more often is these ones where there's some kind of angle between them, and then you'll get this very characteristic arc shapes, where the light source is multiply imaged. So here you've got 3 images, and they'll tend to be along an arc. And here you have one on either side. They're always odd numbers of multiply imaged galaxies, but often some of them are obscured by the thing that's doing the lensing. So in this case, you can see this one here.
Is it on? I always thought it was even.
Sorry?
Is it on? I always thought it was even.
It's always odd. I guess even if you count the original one, yeah, so then it would be even. Yeah, so here we have a 5, and there's a 3. So what this is doing is, not only is it stretching out the image of what we're looking at, it's actually conserving surface brightness. So this means we're increasing the flux. So we're getting more light, and because it's being stretched out, we're seeing things in more detail. So in order to maximize the use of this effect, of course, we need the most mass possible between us and the galaxies we want to look at. So we turn to the largest, most massive gravitationally bound structures in the universe, which are clusters of galaxies. And so we like to think of this as using a telescope that is 10 to the 21 meters across. And we then use our puny little 8 to 10 meter telescopes on the ground as a secondary mirror to collect the light. So what we're doing with this is not only boosting the total flux, but also the spatial resolution of our galaxies. And you can see in this example, these are like really nice, pretty massive arcs along here. So just to demonstrate how well we can do with this, this is illustrating the kind of spatial resolution we can get currently, and hopefully in the future. This is wavelength in microns, so these 3 lines here equate very approximately to the HR for emission line at redshifts 1, 2, and 3. And then our angular size, at the moment with an 8 meter telescope with adaptive optics, we can get down to about a 10th of an arc second, which is about a kiloparsec on the galaxy. So on scales of a kiloparsec, you can see things like these massive starburst regions. But things like normal H2 regions are somewhere in here, around 100 parsecs. And of course, what we really want to do is get down to the limits of like the clusters at 10 parsecs, stars down here at 1 parsec, ultimately. But we're looking here at the moment at the H2 regions. So we'll be able to do a reasonable job of this when we get 40 meter telescopes in the next few years. We'll be able to look at of order a few hundred parsecs in high redshift galaxies, and then obviously what we really want is a 100 meter telescope, so we can do even better. But what we're doing with gravitational lensing is taking our 8 meter telescope and getting the kind of resolution that we will be able to achieve ultimately with a 40 meter telescope, so that we can see things like these H2 regions now. So the way we sell this in proposals is we're previewing the science that we'll be able to do routinely once we get things like ELT, GMT now, and so on. And ALMA if they ever give time to us for high redshift folks. So this is an example of what we actually have to do to get useful information out of a high redshift galaxy. And this example is the cosmic eye, named for obvious reasons. This is, it's part of a cluster, but most of the lensing in this particular galaxy is coming from this one galaxy in the cluster. So this yellow thing is a foreground galaxy, and then the blue one is the arc behind it, which makes a nice eye shape. There's also another lens galaxy in this cluster just off to one side that's a straight line, that's known as the eyelash. It's very creative names. So what we do when we get an image like this, first of all we have to find it, which some people have been developing algorithms to do that, but it's basically by eye. You recruit an undergraduate for a summer and sit them down in front of lots of images of galaxy clusters. We find the galaxy. We then need some detailed imaging of it from HST. So we've teamed up with people at Harold Labeling, the MAX program, to get detailed images of the clusters. But we then have to understand how the galaxy is being lensed in order to correct for the lensing magnification and derive the intrinsic properties. And to do that, we need a mass model. So we go to the cluster, and the way we make the mass models is to take spectroscopic redshifts of as many lensed galaxies as possible. So you can see all the green things marked on here. Over here are lensed images of galaxies behind the cluster. By using the spectroscopic redshifts, we can also identify which ones are multiple images. It's actually much easier to see when you get a colour image, because we'll be able to pick out things that are the same colour. And then once we know exactly how far behind the cluster they are, we feed it into a black box that calculates what mass distribution will give you that arrangement of lensed galaxies at those redshifts. The errors in that are actually surprisingly small. It's an order of a few percent, so for high redshift work, this is not even the dominant source of error. So this gives us a lens model, the distribution of mass within the cluster. We only really care about the dark matter for these purposes because that dominates the mass, which is actually really helpful because the dark matter is also much tidier. It's not quite as complicated and croppy. So we can actually do a pretty good job of reconstructing that distribution. We can then go back to our lens galaxy and unlens the image and derive what it originally looked like before it was lensed. So this is this example of the cosmic eye. This is seen in O2, I believe. So it's the distribution of O2 within the galaxy. This dotted line on here is the caustic, which is the line in the source plane of the galaxy that maps to the critical line, which is the blue line in this cluster in the image plane. All that is the region that's theoretically infinite magnification. So it's also an infinitely thin line, so you
Right,
can
because the
actually
point
get,
source would be magnified.
theoretically, yes. So this one is very highly magnified because of that. And generally, with lens galaxies, you always want to look around about the critical line for that redshift. It varies with redshift, because that's where you're going to get the most magnification. I think the best we've ever done is around a factor of 100. Of course, once you get very close to this critical line, the magnification gradient is also really high. So things that are very close to this line on here are going to have very, very high magnifications, and then it's going to drop off as you go further away, which gets complicated. And I will show one example of something that's actually further away, which in some ways is better because you get less distortion. So we then want to get more detailed information out of this galaxy. So what we've been doing is going to IFUs, and by using an IFU on this galaxy and then reconstructing that in the source plane, you can get the dynamics. So this is showing this galaxy is a very nice rotating disk. It was the first example of a rotating disk of Redshift 3, so it's back in 2008, and a map of where the star formation is taking place inside the galaxy. And in this case, there's only two, but there's still two giant clumps of star formation going on in this galaxy, Redshift 3.
Do you know if the surface is rotating? I mean,
Sorry?
do you know for certain, is it really that smooth, or is it just two clumps, two smaller things that are, this is always a question people give, or is
Yeah.
it dynamical interaction,
So,
or is it?
this is actually an interesting story. We've settled on the idea that it's rotating,
Yeah.
but this was a Nature paper, so it had 2 referee reports, and one referee came back and said, oh, this velocity field is amazing, this is clearly a rotating disk. And the other one came back and said, oh, this velocity field is amazing, it's clearly a merger. So the truth is, it's actually really difficult to distinguish, because if you've got 2 galaxies merging, they're kind of doing that, it looks exactly like a rotating disk. So the best modelling we could do, it looked pretty good. The velocity fields do look different in these lens galaxies to the ones you'll see from things like the SIMS program, because the magnification is different in different directions across the galaxy. So you can see here it's been stretched out in an arc. That means it's really, really magnified that way. It's not really magnified at all in the perpendicular direction. So you don't get the nice spider pattern that you would see in another lens galaxy, which would make it quite difficult to tell. So it's more usual to see these stripes going across. So yes, this is one of the problems we've run into. It is non-trivial to determine if something is rotating. It looks like it.
Well, it is amazing velocity.
Yeah, it is very pretty. Okay, so the spatial resolution in this is about 100 parsecs. So 100 parsec spatial resolution in Redshift 3 is really cool. Of course, the downside of this whole thing is it takes a really, really long time to go from there all the way to here. So it's not like you can do massive samples like the SIMS survey has done, because there's so much more involved. But for this very small sample of galaxies, we can get a lot of information. It's really cool spatial scales. So the first thing that I looked at was the H2 regions within these galaxies. I started off first of all working with Tucker Jones, who at the time was Richard Ellis's grad student at Caltech, because he had done a sample of some of these galaxies with Osiris on PEG. Now this is what happens if you look at H2 regions in the local universe. This is the size versus the star formation rate. So all these black points are local H2 regions from the SINGS program. And this line here is almost a gradient of 2. It's very close to 2. So basically that's constant surface brightness. And if you go above that line, it's higher surface brightness, below is lower. So the high star formation surface density ones are up here. Now if you look at this in the high redshift galaxies, this is the sample. It was a sample of 6 lens galaxies, including the cosmic eye that I just showed you. And these are all round about a redshift 2. It goes from like 1.6 up to 3, which is this one. And if you pick out H2 regions in here, they're all way up here. And this is a log plot, so this is about a factor of 100 times brighter than local H2 regions. Now, there are some things locally that look a bit like that. The blue points on here are all from the local universe. They're things like the antenna, 2 Zwicky 40, 30 Doradus. They tend to be interacting systems, and they're the most massive starbursts that we see locally. But things of that similar surface brightness seem to be pretty ubiquitous in high redshift galaxies. So we wanted to understand what it was that was causing this, and also whether it changes smoothly with redshift. So do we have all these bright things in the high redshift galaxies, and then they jump into here, because this kind of looks bimodal, but there's no physical reason things should be bimodal. So we decided to look at an intermediate redshift and see if we could find things in this middle region here. So we applied for time on the Hubble Space Telescope just after WFC3 was installed. WFC3 has these really nice narrowband filters designed to get some emission lines that low redshift people do that happen to correspond to H alpha at redshifts 1 and 1.5. So this was the sample of galaxies, and this is all observed in a narrowband filter centered on the H alpha emission, and then we have a nearby broadband filter to subtract the continuum. And this is the H alpha distribution in these galaxies. And this is the lensed galaxies. This is without corrected lensing. And you can already see there are these clumps of high star formation. This one here, you can see in the colour image better, is actually it looks an awful lot like a slightly inclined spiral disk. And it's a redshift 1.5. This one here was really unfortunate. It's a beautiful spiral galaxy. And this is the one I mentioned that's a little further off from the critical line. And the geometry of the cluster is such that it just happens to be magnified squarely. So it has the same magnification in both directions, which means it's just like someone has taken it and done that. It's amazing. So you can see all this detail, you can see the spiral arms. So we thought this is going to be a perfect candidate to do this. Turns out it has very low star formation surface density. So all we see, that's actually a diffraction spike from star. All we see there is the very centre of the galaxy. We went back later. I don't think I have time to talk about this, but we did do it with Osiris and went a lot deeper. And then you do still get some HR from here, but it's very, very low surface brightness. So this is what happens if we unlens them. This is what the intrinsic morphologies of the galaxies look like. Now the magenta ellipses on here are the effective PSF in the source plane. So we measure a PSF in the image plane and then test how that's affected by the lensing. And of course you've got more magnification in one direction than in the other. So you end up with really good resolution in this direction, not in that direction. So it means you still get some quite distorted shapes. This is not really that long and thin, it's just got better resolution in one direction. This one though is pretty cool, we've got lots of clumps out of that. This one you can see from the effective PSF that it's almost circular, so it's a shame that you couldn't get rid of that one. So if we select the H2 regions out of here and put them on our plot, for this version of the plot, I actually reanalyzed all the SINGS data to make absolutely sure we were selecting star-forming regions in the same way. So the SINGS images are already narrowband H-alpha images, so they're very similar. I degraded them to be the same resolution as we get in the high redshift galaxies, and then selected the star-forming regions. And you find there down here, the stripy effect there is actually real. You tend to find in any one galaxy that the star-forming regions are all the same surface brightness, which is a known thing. Giant molecular clouds all tend to be the same surface density within any one galaxy. So that gives you the stripy effect.
Is that a gas fraction? Why would that be some kind of
Spoiler.
fractal? I'm sorry.
Yes. My opinion is that yes, it's dominated by the gas fraction. So these are our low redshift star-forming regions. These are the ones I just showed you from Tucker-Jones in blue. In green, I've overlaid some unlensed surveys, these are redshifts 1 and 2. I would take them with a pinch of salt because they're all above a kiloparsec because they have spatial resolution of a kiloparsec. But it's been done, so I'm putting them on there.
Was it UV or H-alpha?
H-alpha. Yeah, which way around this is. The pink ones are from the Scheisel's survey, which is symphony follow-up to Heisel's. And then the green ones are Evelyn Wisniewski's Osiris sample. And now these are where the redshift 1 and 1.5 things lie. So they're kind of in the middle. This clump down here is all from one galaxy, and then these two up here are both from the same galaxy. So you can see again we have this striking effect. That one there is the centre of that, the spiral disk that we barely got, so just got one off that one. So if you fit lines to these, you can measure the average surface brightness of star-forming regions at different redshifts, and you can see that it seems to evolve with redshift, these limited samples. For this sample, I have only included the blue ones, and I've ignored the ones that aren't lensed. So all of these 3 samples are selected on the same kind of spatial resolution. I should have mentioned actually for these ones, rather than just take the star-forming clumps that Tucker published, I took the Osiris cubes and made fake narrowband images out of them so that it was all done the same way.
Excuse me, can you explain the vertical axis? What is that? Star formation rate?
Star formation rate in solar masses per year.
In solar mass, what's the unit?
Solar masses per year.
Solar mass per year, yeah, okay, thank you.
Yeah, sorry, I cut the edge off because it wasn't readable. I didn't put units
Okay.
back on.
So, sorry, what kind of selection effects do you have in that Gaussian plot?
It's actually, it's not on this version, is it? It's in the published version. It's really difficult to tell because the main selection effect is in how do we select which galaxies we're going to follow up to do this. And a lot of that is someone eyeballing a cluster and saying, hey, that looks like a good galaxy, which has a slightly unquantifiable surface brightness limit. It has to have there's a minimum total star formation rate for us to be able to follow up with an IFU.
So, but to be fair, I guess the point is that the envelope, the upper envelope, regardless of what's happening below, right, the upper envelope does include the small dispersion.
Yeah.
That's
Yeah,
right.
I'm absolutely not claiming that there are no
Sure.
low surface
Okay.
brightness clumps in high redshift. I'm sure there are. I know that for the Osiris sample, the limit is down here. So if there were lower ones, we would only see them over here, but then we would expect to see some in the middle as well. For this one, obviously the limit's a bit lower, it's down here. So maybe we would have expected to see this, but it's a small sample, so it's hard to say. And the spatial resolution threshold it varies from one galaxy to another because of magnification, but it's roughly 100 parsecs here and slightly bigger for the Osiris sample. So we made luminosity functions out of these H2 regions. The black one again is redshift 0. Red is redshift 1, which is barely higher than the redshift 0, 1, except for this point out here, the excess at the bright end is completely dominated by this one galaxy up here. So this is number of regions per galaxy with a luminosity above this limit down here. And then the blue ones are the redshift 2 sample. Now, Phil Hopkins has done some simulations of giant molecular clouds in galaxies and said that the mass function should follow, it should be a Schechter function. So we took the Schechter function from his paper with his supposed fainthead slope and mass cutoff. There was an arbitrary normalization, so we fit that to the black points, and that looks pretty good. The mass cutoff seems to agree with what we observed in redshift 0. We then just took that same normalization, same fainthead slope, and evolved the mass cutoff according to his simulations for high redshift galaxies, which I believe in his simulations high redshift just means higher gas fraction, and it just happens to fit pretty well to our redshift 2 sample. So this is suggesting that if all we need to do to explain this is increase the gas fraction in the simulated galaxy, that it is gas that's dominating this effect. So if you think about what's actually causing star-forming regions to form, you've got gas collapsing in a galaxy, and as it falls in, it's falling under gravity, and it's supported by the dynamics of the galaxy. So you've got the turbulent velocity and the rotation within the galaxy. So this gives you the Tumor stability criterion, which is Q, which is just dynamical terms on the top. Kappa is just V over R. People argue over the coefficient, but it's about 1.5. And then on the bottom is just stuff about what mass is in the galaxy. This is the mass surface density. And the different components of the galaxy do contribute differently to this mass surface density, which I'm kind of going to gloss over now, but if you're interested, it's in the paper. But it's dominated by the gas rather than the stars, because of course the gas is collisional. Now, if the Tumor criterion is about 1, then your galaxy is going to be marginally stable. If it's less than 1, it's going to fragment. And it will fragment on scales of about the Jeans length. And if you plug all the variables in, the Jeans mass turns out to be about the mass surface density cubed, kappa, which is just this V over R term, to the -4. So this suggests that to evolve this mass cutoff, I'm using mass and luminosity interchangeably here because the simulations predict mass, we measure luminosity, so we've done an empirical conversion from mass to luminosity. This isn't very certain, but we think we need to make more massive clumps, and therefore what we need is an increased mass surface density, or possibly some change in the dynamics. So we looked at how these things change with Redshift, and as I said, the mass surface density is dominated by the gas component. So it looks like the drivers of these very clumpy galaxies at high redshift are a combination of the evolution of the gas fraction and the dynamics. So that's what we're going to go on to look at. We're going to start off with the dynamics, because we can do that with integral field spectroscopy. Just IFU 101 for anyone who hasn't done it before. An IFU just gives you an image at every wavelength, or equivalently, you can think of it as getting a spectrum in every pixel of your image. So the one that we used 3 different IFUs, NIFs on Gemini and Gemini North. We've actually only done 1 galaxy with NIFs because the limiting factor with these things is you need a good natural guide star nearby to get adaptive optics, and these things tend to be found in very dark fields, so it's really hard to do that. We've used Symphony on the VLT. Of course, we had very easy access to the VLT back in England, and then Osiris on Keck. Keck, we were able to use the laser for the adaptive optics. Symphony does have a laser, but it's really difficult to get time on, so that's all we've done with natural guide star. So Symphony is the one that we've done most of our work with, just of the availability of time for the most part. And this is the sample. We have 17 galaxies now between redshifts 1 and 4. And this is kind of my equivalent of the very pretty Sims slide, where they have much larger sample. So we have a group of these that we believe are dominated by rotation. And as I said, take that with a pinch of salt because it's very difficult to tell. These ones all here are at least consistent with rotating disks with high turbulence. So the ones up here are the most rotating. This is that spiral, the one with the nice square magnification. Once you do it with Osiris, you can actually get that H alpha out. And this one here is a really, really nice, bright galaxy, Redshift 2, that's my favourite one. Some of these were done in 03 if they were the wrong redshifts to get H alpha. And then down here we have a few that are more consistent with being mergers, because sometimes you get a very steep change in the velocity. And then there's this one here, which we've classified as dispersion dominated, which is a classification that, stop looking into that, SINS gave to about a third of their galaxies. We've only given it to 1. And the reason is this galaxy is right on the caustic of that cluster, and it's doubly imaged, so it gets folded over the critical line. And that means you're missing part of the data, because there's a fold, and where the join is, you can't see that part of the galaxy. So it is entirely possible that there's a velocity gradient in this galaxy that we can't see because we don't have enough of it. We've tried using the third image, which is isolated, to estimate how much of the galaxy we've missed, but it's not magnified enough to get sufficient resolution to be able to tell. So I'm hedging by calling it dispersion dominated. I would actually not be surprised if there's no such thing as a dispersion dominated galaxy. So one of the obvious things to look at when you look at dynamics of high-redshift galaxies is the Tully-Fisher relation. This is some of the work that's being done at various redshifts. Basically, the conclusion in the literature is there's no conclusion on the evolution of the Tully-Fisher relation. Some people believe it's going to move in this direction at high redshift. Other people believe it moves the other direction, which seems to depend on what importance you give to baryons in your simulation. So the gimmick example I put on here thinks that the 0 point should go down at high redshift. The stars are all my sample. The filled ones are the ones that I think are rotating disks, and then the unfilled ones are mergers or uncertain. These two actually have high doubts about the stellar masses. They're already published stellar masses, but they don't look all right to me, so I'm not too worried about those. But even so, you can see here there's huge scatter. It's not inconsistent with being exactly the same as the local relation, but it's certainly not tight enough to be able to make any conclusions about the evolution. What's interesting though is I said that the thing that dominates the simulations is how much importance they give to baryons. So I thought, well, people always interpret the Tully-Fisher relation as being a relationship between the stellar mass and the dark matter. So you've got stellar mass on this axis, and then the velocity along this axis is supposedly dominated by the dark matter halo. So this is often reported as a stellar mass versus dark matter mass plot. But I thought, well, what if there is no dark matter? These things are really, really small. They're a couple of kiloparsecs. We normally ignore dark matter when we talk about the dynamics. So what if we just take the y-axis and assume that the velocity is entirely stellar mass driven? So divide it by the radius, so just v equals gm over r, and you actually get a pretty nice fit. So the information we're getting out of these galaxies is entirely consistent with the dynamics being completely driven by the baryonic mass. Of course, there's going to be some intrinsic scatter in there because there's gas as well as stars, but it all seems fairly consistent and also systematically different to these lower redshift things. So these are either lower redshift or they're much bigger so that you can get spatial resolution without lensing. But of course, being bigger means, of course, you're measuring the velocity at a larger radius, and so you are more likely to have dark matter in there.
So you're saying that within these enclosed radii, the dark matter fraction is less than that at lower redshift?
Yes. Well, it's not the same radius.
Sure.
So the radius we're measuring this at is 2.2 times the half-light radius, which is the one that seems to match the best with the radio data at low redshift. At high redshift, though, the things are so concentrated, the half-light radius is less than a kiloparsec sometimes. So the physical scale on which we're measuring it is much smaller. So I just don't think these samples are comparable.
But even the Milky Way seems to be exploring maximum small, right? Like in the inner couple of kiloparsecs, the stars can account for all of that. So this would be nominally consistent with what we see.
Yes, absolutely.
So I think,
Yeah.
if I'm in the dashed line, that is actually GM over what the R
Oh,
is,
yes,
or
this isn't
something
a
that's-
fit. This is,
That's
the
a
dashed
predict-
line is just
That's,
GM
that's,
over R.
Isaac Newton
Yeah.
predicted that.
Yes,
I know
it
it's
is.
true. And then gas fraction, higher gas moves you up,
Yeah.
and dark matter moves you down below.
So my only conclusion really on the Tully-Fisher relation is don't believe the Tully-Fisher relation at high redshift if you're talking about dark matter. I think we're going to need to be able to get much larger galaxies or measure a much larger radii before we can say anything about that. Which is actually pretty similar to what Sarah Miller has been finding. She's been doing Tully-Fisher relation with long-slit spectroscopy at high redshift. So this appears that the dynamics then are dominated by the baryons of the galaxies. So that's just a quick digression. I'm going to go back to star-forming clumps now. If we pick clumps out of these galaxies, there's lots, so this plot gets a little messy. The grey now is redshift 0. These kind of faded red things are the HST narrowband sample, redshift 1 to 1.5. And we now have huge scatter going upwards of brighter things. They're colour-coded by redshift, and then I've divided them into bins to fit the average surface brightnesses in each redshift bin, and you can see there is a general evolution upwards. Again, these are only the brightest clumps in the sample. You can see we go from redshift 0 here, 1 to 1.5 here, which includes both the narrowband HST sample and the lower redshift things from the IFU sample. And then 1.5 to 3 is about here, and then greater than 3 is out here. This doesn't count the things that are now kind of dark yellow, which are the unlensed samples from other surveys. So it looks as though we're continuing this evolution to higher surface brightness out to higher redshift. We've now gone out to about redshift 4 in this sample. And just briefly, we did also look at the velocity dispersion in these clumps. This is something that some of the unlensed surveys have been doing, things like Scheisels. And they claim that what tends to happen is you get this cloud of points at low redshift and a cloud of points at high redshift, and people draw a line between them and say, ooh, evolution. And the evolution that you expect, or that has been published by other groups is shown by this shaded region, which you may or may not be able to see on the projector, and this dashed line. But you can see you can basically do anything from like that to that with this data. So if we put our lens galaxies on top of this, it just does that. Now the dotted line that goes straight across is the resolution limit of the symphony, which we derived by doing lots of fake emission lines and testing at what velocity dispersion we could reliably recover the input light with. It's basically about 50 kilometers a second. And if you look above that limit of 50 kilometers a second, you get a wide range of radii and luminosities. There doesn't seem to be any relation. So this is just another word of caution about unlensed surveys, which have not only this be the same velocity dispersion resolution limit, but also their radius limit will be much higher, around about here. So it's unsurprising we have a group of points up there, and then also the luminosity limit is going to be up here. So I find absolutely no evidence for evolution in velocity dispersion.
It's great because it's probably more important to look at the colors as coming from the same galaxy rather than any trend in redshift.
Yeah.
Right, as I said before, the clumps tend to move together.
Yes.
Okay,
Yes.
so that's why I say that.
Yeah.
Okay.
Okay, I'm going to skip over the eyelash because I'm going a bit too slowly. But basically the eyelash was done, it's a sub-millimeter galaxy that we did in the radio, and you find the same thing with white clumps. So we look at the evolution of star-forming clumps within galaxies. We can predict from simulations, this is all using gal form, how we would expect star-forming clumps to change. So if we're plotting the surface brightness of the clump versus the mass of the clump, remember into the mass we predict just based on Astronomy 101 gas collapsing on the Jeans length with a Tumor criterion of about 1. This is going to be related to the mass, surface density, and dynamics. So we can predict from simulations roughly how those things are going to evolve with redshift. The clump surface density is just coming out of this plot. It's just the 0 point of fit with a gradient of 2 to the star formation rate surface density plot. And we can get out of simulations how we expect each of these things to vary with redshift. And you get a line that looks like this. This is how these two quantities should be related in different galaxies. And if I put where the different redshifts are on top of here, you have redshift 0 is the point down here. Redshifts 1 to 1.5, you get this region. 1.5 to 3 is this blue region. And then 3 to 4 is the pink region. Most of the width of that is uncertainty in how gas fractions evolve with redshift. So we looked at the predictions from Galform and also the empirical relation from Jim Beach a few years ago. It's all really uncertain because there are so few measurements of molecular gas at high redshift. But generally, it looks as though gas fractions evolve as 1 plus z squared. So it's 1 plus z to the 2 plus or minus a half gives you the width here, and then 2 quantities should go up like this. And if we put our points on top of here, it's fairly similar, given the number of uncertainties and the simplification of the assumptions. We do find our redshift 0, that's not normalized or anything, it just happens to be in the right place. But of course, it's also a larger sample. 1 to 1.5, it's maybe a little bit higher surface brightness, but it's definitely consistent. And same with the other 2 points, consistent with what we expect from simulations. So this is telling us that so far all the data suggests that these galaxy properties are being driven by the gas fraction and the dynamics. And it's mostly gas fraction. The dynamics actually evolve relatively little with redshift compared to the gas fraction evolution. So we can actually look as well at how our data compare with what we predicted to be the evolution of these quantities. So kappa, which is the V over R, very, very small sample size. And you can see there's an awful lot of scatter, but if you bin them up into redshifts, you can see that our 3 redshift bins are kind of consistent with the line, which is what simulations predict should be the evolution of redshift. The mass surface density, again, lots of scatter, but general progression in the right direction. And then gas fraction, this one is even more uncertain because we have not measured the gas fraction. What we've done is invert the Kennicutt-Schmidt law using the star formation surface density, which is what everyone else does. I really don't like doing because even locally it's been demonstrated the Kennicutt-Schmidt law doesn't actually work on very small spatial scales, but if everyone else is doing it, then so can we. This dashed line here is Scalform, and then the blue shaded region is Jim Peach's empirical relation. And this point out here is one of our lensed galaxies at Redshift 5, where we actually have measured the molecular gas from the CO5 to 4 transition. So you can see again we're kind of generally consistent with this idea that's building up from high redshift molecular gas observations that the gas fraction rises with redshift and then seems to tail off above redshifts of 2 or 3 or so, but very, very small number statistics at the moment because this is not done well.
Can I ask about the Galform prediction?
Yeah.
This must be for some mass range of galaxies.
Yes, it is. Which one did I choose? It was for, it was a halo mass size, I think.
Which was a halo mass size?
Well, yes.
Something a little bit smaller than Milky Way, perhaps?
Yes.
Okay.
Yeah. Cedric Lacey gave me 3 lines and I picked the middle one. But there was actually very, very little difference between them, which is why there was no point putting all 3
Really?
lines.
As soon as you get to larger, even the Milky Way, I would debate is very low gas fraction at present.
Yes, it's about 10%. We know Milky Way.
It's probably not, that's probably in the right ballpark, okay. But here it's 30% present, although a lot of times we
Yeah.
squished there at the last.
How average is the Milky Way in terms of gas fraction? Actually,
Oh,
everything
let's talk
else
about that
is
over lunch.
Yeah, okay.
I think the Milky Way is very abnormal.
Yeah. So I'm going to skip over this a little bit and just show the answer. This is the lens galaxy Redshift 5 that we did molecular gas in. This is with the Plateau de Beure interferometer in France. This is the most beautiful spectrum you'll ever see. It's 3.5 to 4 sigma in so many simulations. You can get anywhere in that range. Detection of the CO5 to 4 emission line at Redshift 5, which does make it the highest redshift non-quasar molecular gas detection. But that spectrum is the reason that other people aren't doing this. It's still really, really hard. Until we can use ARMA, which they're not letting us do. Not that I'm bitter or anything. You sort of got ARMA time. This is good.
No, sort of.
Sort of.
Maybe.
There's a combination.
Yeah, is that right?
So this is that same gas fraction evolution with redshift plot. So we have one point in here. These are some other SMGs and things that we've done. So with Plateau. This is something that hopefully we'll be able to fill in, we being the community as a whole, over the next few years with ALMA. This is just showing the Kennicutt-Schmidt law. Again, 1 galaxy to add to this plot at Redshift 5. Genzel's group will have you believe that some millimeter galaxies lie above the local Kennicutt-Schmidt law, but I'm not going to go into this, but there are so many uncertainties with how you convert CO to molecular hydrogen that I'm somewhat dubious about this. Certainly as far as this 1 galaxy is concerned, it's fairly consistent with being the same as the local relation. So I'm going to very, very quickly, in 2 minutes, just introduce the Hubble Frontier Fields program. This is a director's discretionary time program on the Hubble Space Telescope using 840 orbits to image 6 galaxy clusters in order to find lensed galaxies behind them and hopefully get up to much higher redshifts. We're looking at redshifts greater than 7 now to try and see galaxies in the epoch of reionization, using the benefit of the gravitational lensing to magnify them. These are the 6 clusters that have been chosen. I like to show where they are for a really, really geeky reason. This is the first cluster, Aval 2744. We now have most of the data for this one. The final data is due to come in within the next couple of months. There's already been a flurry of papers on this cluster just using the partial data. many more over the next few months. And then MAX 0416 is located just here off the constellation Eridanus. And some of you may know this double here in Eridanus. That one there is where Vulcan is. I really think who appreciates that. So the great thing about this program is it's making use of the fact that you can use both WFC3 and ACS to get good wavelength coverage from the optical or rest frame UV, rest frame far UV out to the infrared, which is still rest frame UV in the galaxies we're interested in. So this is the field of view of the Hubble Space Telescope. You have WFC3 here and then ACS over here. So as well as looking at these galaxy clusters to get to the lens things, they're also using the other camera to look at a completely blank field that's never been imaged before at the same time. So you can look at the galaxy cluster with WFC3 and this blank bit over here with ACS. And then 6 months later, it flips around and we do the galaxy cluster with ACS and the parallel field with WFC3. So as well as getting these awesome gravitational lensing images, we're going to be getting 6 new effectively ultra-deep fields. These will be some of the deepest images ever. They're getting down to about magnitude 29. So we'll be able to do lots and lots both with the lensing and with unlensed galaxies. So this is some of the data that's come in so far from Aval 2744 and the parallel field. A really nice galaxy cluster over here and a really nice blue blank field. The blank field doesn't have WFC3 yet, so we haven't really done anything with that, but that's due to come in at the same time as the optical data in the cluster later this spring. So this is a zoom in of the cluster. We show the light in red, the mass in blue, and then the magnification in red. It looks like this. This is the critical line, I believe, of Redshift 7. So what we hope to find is lots of highly lensed galaxies around that critical line. We've got to zoom in. We have to zoom into this region here, and you can see these things here. These long things are all lensed galaxies. There is a bit of a problem with this, though. This is some of the work that's already been published. So 3 papers all on the same galaxy so far this year. And this is this group's source selection at around Redshift 7+. And you can see there's this weird cluster thing going on up here, which I'm not 100% convinced by yet, because this is right at the edge of the WFC3 image where it gets a bit dodgy. But there's very little going on around here, around the critical line, which is where we get the most magnification and therefore the most benefit of gravitational lensing. And so this is actually becoming a bit of a problem with this program. We said we were going to get all these amazing faint lensed galaxies, but there's a great big bright galaxy cluster right in the way of where we want to look. So the thing that I've been working on is trying to move the cluster out of the way. So if we take, this is the H-band image of the cluster, and this is my source selection at Redshift 7+. So far we don't have the deep optical imaging yet, so it's still quite uncertain, but these are the sources that have greater than 50% probability of being redshifts higher than 7. And you see the same problem. There's nothing really in the center here, there's a couple here, but nothing really in the region where we're getting the most magnification. So I've been working on using wavelet decomposition to subtract anything on scales larger than high redshift galaxies, so anything in the foreground. And this is the result. It looks a bit messy, but it gets rid of a lot of the intracluster light that's hampering us in the center. And this is the new source selection, using this as a detection image. And you can see we now get a lot more high redshift sources right in the center of the cluster, all around this critical line where we're benefiting the most from magnification. And this is all really preliminary. I did this in a day for an HST proposal, but it's really promising. We've been running some simulations to test how good the depth is. If we use the raw H-band image, this is the effective depth across the image. And you see it goes up to 29.5 magnitude is the yellow one here. But we're losing several magnitudes right here in the center, which is the region we want to be looking at, just because there's all this intracluster light and bright things in the middle. If we use the wavelet subtracted image though, this is what happens to the depth map. We now only lose the very, very centre, and we're also getting much better depth all the way across the field. And this is just showing the difference. So we have massive improvements here in the centre, but then some improvement all the way across the field. So this is hopefully going to allow us to see all the faint galaxies that we claimed we were going to see as part of this program.
So I'm using Galfit to subtract the galaxies and then try to model the
This is actually,
It
I
looks like
do-
many of them are pretty poorly modeled.
yes. Yeah, this is just doing the wavelet subtraction. So you get some really nasty residuals left behind, which I'm probably going to model and subtract to make something pretty enough to go in the paper. But essentially, we're not going to get anything that's right here in the middle. That's probably spurious anyway. So I could model them to subtract it to make it look prettier, but I don't think it's actually going to.
I was
lose
just
too
talking about
much.
center, I was talking about the objects outside.
Yeah.
On the outside.
It's a wavelet thing, so.
Yeah.
I think she's right, it's a, you know, how much is it actually affecting your ability to recover some sort of, it's probably more of a question.
So I have, I played around with using Galfit to subtract the residuals. Galfit doesn't model residuals very well because they're not physical, they don't look like galaxies. But I have been playing instead with shapelets, which are something that weak lensing people use to parameterize like statistical distortions in galaxies. But it just so happens that it will fit completely random shapes, which is what I want. And that's actually doing a much better job. So that's what I'm going to try to purify the image a bit.
Just remember, one of the guys I talked about earlier, the Slacks team, Adam Bolton was using something, some sort of weird two-dimensional B-spline fitting, which was doing an exceptional job of subtracting off
Oh,
Galfit.
really? Okay.
Yeah, but we'll talk about it later.
Yeah. So there are a few tricks that people use to subtract this. So my intention is to try them all and
No, it's still really promising, I think that's the most important thing.
so yeah, I'm sorry that I've gone a little bit over time, so I'm just going to leave my conclusions up. Thank you.
Great. Thank you. More questions for Rachel?
How do you confirm those galaxies now behind us?
Oh, so then that's really hard because
what about
normally we would go and get a spectrum.
But you can't get rid of the galaxies on the spectrum. I mean, if you're
Yeah.
the emission lines,
Yeah.
that's one thing.
So yeah, the fainter things we're never going to get spectrum on. So I think for this work it's always going to be trusted relativities.
I was thinking another good thing to do here would be Mark Skisson talking about doing an image flip, assign a negative sign to everything, and then you go back and after you've done the subtraction, just take the inverse of the image and rerun your detection algorithm. That might give you something. And the residuals are going positive and negative.
Yeah.
I just think that because then you've also just been worried about wavelength dependent effects. It's
Yeah.
really, this is what you need to do. I think you're doing the right stuff.
So the thing
Which
that
way-
I've
how you
been,
gonna confirm this?
my original intention was to use the wavelet subtracted image to detect galaxies, but it took all the photometry on the original images. It actually turns out from the simulations we've done that you get not only deeper on the wavelet subtracted images, you also get more accurate photometry, which surprises me, and so I want to test that a bit further before I claim it too much. But it does seem like it's actually doable.
Right. It's not immediately obvious why that would be the case. But
I guess maybe we're doing a better job of the background subtraction. If
Probably
it's-
triggers the background gradients,
Yeah.
so you're taking that out, which simple angles are source
Yeah.
extract would be nice.
Yeah.
Sorry, that's interrupting.
I mean, it would be slightly easier for low redshift bright galaxy. So if you subtract the cluster, and if there is a more distant galaxy, high redshift galaxy behind that cluster. So for low redshift, so just to test, just for a test case, because if you see a foreground low redshift cluster, you will detect the continuum.
Yeah.
Maybe for high redshift, which is
Absolutely. I
more
think
favorable.
I haven't done this yet, but the obvious thing to do for everyone who's working on the frontier fields is to test how well we're doing at predicting the redshifts of the things that do have species. There's huge numbers of campaigns going on to get spexies as many as possible to do the lens modelling. So we already have a catalogue we can compare to.
So you're probing 100 parsec scales, but for some of these galaxies you only have 2 points and 10 points when you're looking at the H2 regions. So are you only seeing like 200 parsecs of the galaxy being lensed, or what's the radius you're looking at?
The radius of the galaxy as a whole is a few kiloparsecs usually, and the clumps themselves inside are often only 1 to 2 parsecs. We are actually looking at doing some of that work in the frontier fields as well, which I didn't show because we have sampled 1 galaxy so far. But there's a really nice Redshift 7 triple image system, which is the, I think, highest Redshift. Maybe you have specified non-quasar, I'm not sure. Multiple image system seen. We were really excited when we found it, and we have a grad student working on doing spatially resolved SED fitting. And we kind of undenied about doing a single object paper, but I think we're all getting really tired of the papers that are coming out of frontier fields that just say here's galaxy and do zero science. So we thought, no, we won't do that. And then someone else did on the same system, so we got scooped on that. So I guess that's the price you pay for trying to do science.
Price of paper choice, well said. Okay, I hadn't scheduled graduate student harassment yet because I wasn't know the exam schedule. If I did it at 3:15 in Munderland, would that work?
Their exam is
We
at
have our exam at
3:30.
What exam?
So
Oh.
okay, so should we do it? Can we do it? I think at 3:45 or so. Would that work?